away you are from me and my difficulty in possibly being able to see some of you, I might not do what I've done other times I've given a talk where people are sort of more close in. When they're closer in, I encourage them to just raise their hand and I'll stop and answer a question right off. If you think it will benefit to interrupt me, just yell. I mean, I'm not going to see a raised hand. I would prefer to have a question right as I'm trying to clarify something, so that it's easier to follow rather than have to go back to it. So I encourage you to do that. As I was telling some of you, yes, and as Angelise said, I've been in the field a very long time. It's actually 30 years. And I graduated from Drexel University. My advisors there were really pioneers in this field and had done an awful lot with what was called just fiber optics then. At the time, there was debate over whether fiber should have a single optical mode in the core or support many optical modes. You can still buy multi-mode fiber, but obviously the single mode one out. That's how long ago we're talking. And there wasn't this division between analog and digital because very few people use digital signals over fiber, and that's now laughable. And that now microwave photonics is sort of the poor younger brother. It's almost all fiber optics is used for the digital market, the telecom market especially. And so what is involved in using photonics in the analog realm is this very small niche field that still only has maybe 500 researchers around the world doing things, and I'm going to try to cover a lot of what they're doing. So what this presentation is about is, again, that intersection of the microwave field and the photonics field, where I use photonics, as I think many people do now, to mean something broader than just fiber optics. When I entered the field, that's what it was all called, fiber optics. If you were in photonics, you were pretty much in fiber optics, because fiber was this wondrous new, pretty new invention, and there wasn't much integrated photonics, and free space stuff was still called optics. So, so who wants to use photonics to move microwave signals around? It tends to be people who are dealing with systems involving antennas, and you'll see why that is. So almost all the first part of my talk is about antenna systems and how to use microwave photonics or analog photonics in that realm, in that type of system. And I was going to go somewhere further with that thought. Well, you'll see why that is. Oh yes, the talk has kind of two big sections to it. And the first part is a section about systems and why you might use microwave photonics technology in systems. And then, and this whole part of the outline is that. The second part of my talk gets more down into the nitty-gritty of, well, how can you make a microwave photonic system work really well? What are the devices that need to start working better, and what have the people been doing to try to do that? So I'm going to start with systems, as I mentioned. And so I graduated from Drexel, and then I went to work for GE Electronics Lab in Syracuse, New York, that wanted to start using fiber optics, as they called it, to send signals around, because they had all these big electronic phased arrays and wanted to bring signals together from a lot of antenna elements and that kind of thing. And then I was at MIT Lincoln Lab before my boss and I spun out this company, Photonic Systems. And all that time, who have our customers been? Well, we've had some civilian customers. I forgot I have a pointer. Oops. We have some civilian customers, and actually Photonic Systems' first customer was a civilian customer, and that customer was not the Ackerman large millimeter wave array. I'll get to that. Our first customer was the Institute for the Search for Extraterrestrial Intelligence, the SETI Institute. They had this array of radio telescopes in Hat Creek, California, very remote area, and wanted to bring all the signals from these very remote dishes all together at one point and very far from the array, because if you're doing radio telescopy, you want your radio telescopes very far from civilization, because they're so sensitive. You have to make them so sensitive. Any human-made signals are going to spoil the ability to see what you're looking for. And this is the extreme example of that, or one of, there's going to be more soon. But this is an array of radio telescopes that works over this amazingly large range of frequencies, looks into space and detects things going on in this huge range of frequencies. And it's located at Ackerman. I would never have known where this was. It's a desert in Chile where it is believed, there is no evidence that it has ever rained. So as you can imagine, that's pretty far from any civilization. So fiber optics is very useful in bringing signals from these arrays back to where people are looking at the signals. And then it's not a coincidence that this is a smaller photo than this one. To keep our company afloat, as it were, we really are addressing the needs of the DoD, and particularly the Navy, and in some cases the Air Force, who have, again, antennas, not radio telescope antennas, but antennas in the microwave regime doing either communications or radar. And those antennas might be situated, as you can see from these little white dots, at the top of masts, where you can't put a lot of other hardware, and yet where you really need good high fidelity access to those signals. What is involved in these antenna systems? Well, there's some antennas that transmit information and then some that receive. I'm going to show the receiver front end because it has a lot of interesting components that I'm going to touch upon. Throughout the talk, I use color to indicate frequency in some way. Like, for instance, red might be the lower frequencies and violet the upper frequencies in some broad bandwidth. But I'm talking about, in this case, microwave frequencies. Even when I use color to indicate different optical frequencies, I'm never actually talking about the visible light frequencies because those don't propagate so well in optical fiber. It's the near infrared that the telecom market uses that my community also uses. But it's useful to use a color code to kind of indicate low versus high end of the band. So this is perhaps a broadband antenna trying to receive a very broad range of signals. And what you want is to digitize pull off the ones and zeros if it's a communication signal, or even pull off the code that might be on, the encoding that might be on a radar to improve its sensitivity. There's probably digital information, and that's why the last step here before you go to the receivers is analog to digital conversion. But in between the antenna and those A to D converters, a lot needs to happen. First of all, the A to D converters don't work across this huge bandwidth, perhaps. They may only, do I still have the pointer? Let's see. They may only work up to, say, 500 megahertz or maybe a gigahertz, but more likely down towards 100 megahertz. Whereas my antenna might be up at X band or even above that and be a very broad range of frequencies, where maybe each of these little carriers are, maybe the carriers are 100 megahertz apart. So I want to look at just 100 megahertz chunks one at a time at individual receivers. So I have to do a bunch of things. I have to channelize those, send each channel to a different A to D, and then down convert them each to baseband before the A to D. But prior to either of those things, there are these two other functions that sometimes you need, not all the time, but particularly the DoD tends to need these things now because the spectrum is so crowded, and sometimes it's crowded even with signals like you saw on that ship that had so many antennas on the top. Some of those are transmitting right in the band that this is trying to receive, at these two frequencies, the orange and the yellow, the orange and the blue frequency, and very strongly and very nearby. And that makes it very hard for a receiving antenna, probably listening for something from very far away, to hear that. So that's what this first step then means, suppress interfering signals. And interfering is a funny word when it's our own signal, but that our own signals can interfere with us just as badly as non-cooperative ones. So that's a step that's very important. Another thing that can be important, and now if you think back to that civilian picture of the radio telescope array, when you're doing array beamforming, trying to steer a beam in a particular direction, this antenna might be receiving a signal, and these other antennas might be receiving, elsewhere on the ship or elsewhere in that Atacama Desert, receiving the same signal, and I want to compare what's going on at this receiver with this receiver with this receiver, and if I phase up the signals the right way, I know that any signal I receive came from this direction. That's phased array beamforming and can be electronically steered. You'll see there's people who really wanted to do the steering using photonics technology. I'm going to get to that. So these are all the little steps I'm going to be starting to talk about. But what...
Dan, can I?
Oh, yes, please do.
I was going to ask if you were going to say more about suppressing the interference.
I'm going to be saying more about each of these boxes. And it's funny, that one probably the most, because we're getting some business from that. Well, why not perform all that stuff right up at the antenna? And why bring microwave photonics into this? Why aren't all those boxes sitting at the antenna? And I kind of alluded to that already. Here because the antennas are in the middle of the desert, and here because they're up on a mast of a ship. And all that hardware takes a lot of DC power and is large. And if it weren't, then yeah, I could do all that stuff, and what would come down the mast or come through fiber in the desert would be digital signals. But no, there's times when you really need the microwave signal to be sent over a distance, and the solution for that is what's called antenna remoting technology, which again doesn't yet need to involve photonic links, but you'll see from the next few slides why we have customers who do want it to do it that way. So I've mentioned broadband antenna systems and receiver front ends. Now I'm going to talk about, well, what's antenna remoting and why use analog photonic links for that? Because that's the first step in doing all that other stuff photonically too. So why use photonic links for this? Well, first of all, what is antenna remoting? It's trying to move all this stuff far away from where the antenna is situated. And why use photonics for it? Well, this is a pretty good visual for why you might want to. These are the same lengths of optical fiber versus a certain type of coaxial cable. I couldn't tell you exactly what type, but this is, I can tell from the width, from the diameter, it's not probably the best performing type that you can get. And even if there weren't other performance issues, you can see the size and weight comparison. But another very important thing, especially in a crowded EM environment, is the fact that optical fiber is glass. You put it in your EM environment and it barely affects the EM environment because of its being glass and because of how small it is. And it doesn't emit anything out of its walls or pick up anything through its cylindrical surface. So it's a terrifically secure way of sending signals, and without picking up things you don't want it to pick up, or putting things out there that you don't want it to put out. And then lastly, and perhaps more famously, it has such low loss compared to coaxial cable. So this is a slide, and I imagine these numbers aren't very visible from out there. This is attenuation in 100 meters in different brands of coaxial cable, if you will, across frequency. And this is 10 megahertz, and this is 10 gigahertz, and the three decades in between. And you can see these are likely, thinnest and thickest. It's probably not quite that simple, but the smallest, lightest coax cable is probably going to have the worst loss. And the more you do to shield things and so forth, this is going to be an expensive and heavier cable down here. And even this one at a gigahertz here has almost 10 dB of loss in the 100 meters. And it's much worse as you get up towards 10 gigahertz. Compare that to optical fiber, and it's a little hard to do the one-for-one comparison, because obviously in optical fiber, those microwave signals are on an optical carrier, so now you talk about the loss at the optical frequency. And the optical frequencies are equivalent to these wavelengths, and for whatever reason, the photonics community adopted wavelength as the way to talk about things rather than frequency. So the optical fibers were found to be able to be made optimal in this region here, which is why I say it's not visible light. It's more like around 1500, 1550 nanometers, where things are the most advantageous in terms of loss, and as it turns out, dispersion as well. It's been engineered for that. And that corresponds to about 200 terahertz. So if you're putting you know, even 100 gigahertz of information on the 200 terahertz optical carrier. That's a tiny percentage bandwidth here over which you have this tremendously low loss. In 100 meters, it's less than 1/10 of a dB. And obviously the digital telecom folks want to know, well, no, what is it in 100 kilometers, not in 100 meters? But for our customers who just need to do antenna remoting, 100 meters may be very typical. Our first customer, like I said, Hat Creek, no, they really were going to kilometers, but that is more unusual. So that's why you might want to do analog antenna remoting. And you might want to use what's called an analog photonic link for that. How does that differ from what the telecom people are always doing? Well, telecom people are trying to send digital signals, and so, you know, digital signals extend pretty far down towards DC, so I show them like this, like a baseband type signal. And what you're doing in a photonic link that involves an optical source, usually of, you know, just an optical carrier that comes from a CW, so a source being operated CW, it's usually a laser diode. A modulator, which I represent as a mixer because it is a mixer, it generates these two sidebands, information sidebands on the optical carrier that came from the source. And then there's the photonic propagation medium, often optical fiber. And then the photodetector is also a mixer. It beats, these signals beat against one another, and all that can come out is the low frequency difference signal back at baseband. So that's the digital photonic link. An analog photonic link differs from that because now you may still want the digital information to be what's conveyed, but you put that first on an RF carrier, and then that's what modulates the light, and that's what you recover at the other end. And you know, this looks like a complicated thing to do, but you can see now why I'm talking about antenna systems so much. Because in an antenna system, that is what has happened at the other end of the antenna link. You know, somebody has transmitted information on an RF carrier, and that information may be digital or may be analog, but it's on either side of the RF carrier. Oh, I'm so sorry. I forgot to turn this off. Oh, and it's telemarketer, no less.